Hello viewers, welcome back to the course. So today we are going to deal with the lecture number 15. So in the previous lecture we have discussed about the Newton-Raphson methods for system of equation. Now in this lecture we will discuss about that how we can find the complex root. Of a equation that is my fz equal to 0. So suppose my equation is this one fz, where I can write my z is equal to x plus iy. So my z is the complex number, and suppose I have the equation of this type. So for example, I have my fz is equal to maybe z square, or I have this is equal to e raised to power z. So this type of equation, suppose I want to solve. For example, I can write my f is equal to x plus iy, and then suppose I have z square. So that is equal to x plus iy whole square. So I can expand this one as x square plus iy square plus 2xyi, and based on this one I can write my x square minus y square. So this is the real part, and then I can write my I 2xy. So that is my fz in this case, and this is equal to 0. Now suppose I take the real and imaginary part. So from here I will get my x square minus y square equal to 0 and 2xy equal to 0. So based on this one, if you see from here, then I can write this equation as a function, a new function. So maybe I can I can write this as a capital F, and this is also capital F. Okay. So this is I can write as a capital F. So that is capital F, and then this is I can write as a small f. So I get this equation fxy equal to 0, and from here I can write my gxy equal to 0. So what is this? It is just the system of simultaneous system of equations. And in the previous lecture we discussed that how we can find the root of a system of equation. So based on this one I will find the root of this equation, and I will substitute the value here, and then I will get the roots for fz. So based on this one I am able to find my value of x plus iy. So I will get the value of xy which is satisfying this relation, I will get the value of xy which is satisfying this relation, and I will substitute back. So I will get the value of x and y such that I am getting this equal to 0. So that is the way we can solve the system of equation. So and we know from the theory of complex analysis that any function, maybe it is an analytic function, I can write this function always in the form of fxy plus I gxy. So based on this, that I can always write a function in this form, then we can put this equal to 0, and then we can solve this equation. From here I will get the system of simultaneous equation, this equal to 0 and gxy equal to 0. And using the Newton-Raphson method for system of equations, we can solve this system, and based on this one we can solve this value of this. So that is how we can find the complex root of the equation fz equal to 0. So this is all about that how we can use the Newton-Raphson methods for finding the complex roots. Now let us start doing the code, that how we can make the code for whatever the method we have discussed, because in the previous classes we have just taken the bisection method, we have coded the bisection method using the MATLAB code. Now we will make the codes for maybe fixed point method or regular Falsey method or secant method or Newton-Raphson method. So, let us write the code for this one and go to the MATLAB command. So, if you remember, then in the previous lectures we have discussed the bisection method, and we have called this bisection method from the file, this one, and so I will go back to this, open, and I will go to the directory which we have created last time. So, this is a MATLAB code for scientific computing. So, in that case we have started this code. So, now this is the code we have started with, and I suppose I run this code, change folder, and then based on this one I got the solution. So, in the previous lecture we have started with this one. So, bisection method gives you the solution with the 19 iteration, and that is my initial guess. A is equal to -2 and B is equal to -1, and based on this one I get the value of the root, negative root, and that is -1.86388. So, that is the way we can find the root for this one. Now, today we are going to start with the another method. So, let us start with the new file, this one, and today we are going to do for the fixed point methods. So, let us write the function and suppose I will today I will get the root. So, I will get root, then f root, the value of the f at the root, then number of iterations, and I am introducing the new argument here, and that is the x list. X list means that in the previous class we have discussed that how we can find the order of the convergence of the method. So, but to find the order of the convergence of the method I need en, en minus 1 and en plus 1. So, 3 values, the error at the 3 points I needed. So, I will introduce this one in this lecture. So, that is the output I want, and that is equal to, so I will write that fixed point. So, this is the fixed point method I am going to get. So, what I need to do, I will pass the f value, then I will pass g, then I will pass dg, then initial guess, and then the tolerance. So, what is my f? F is the equation I am going to get the roots. G is the function we are going to write as, so I can write that here, that f x equal to 0. So, this is the x is the root, is a root. So, fixed point means I need x is equal to gx. So, this I need to find. So, I will convert this function into the x into gx form. So, that is my gx. Now, I also know for the convergence I need the modulus value of derivative of g at initial guess. So, this is my suppose initial guess. So, that should be less than 1, because we know that only then the iterative methods, because fixed point method is iterative method. So, in that case the iterative method will converge. So, in that case, so this is my dg, dg means the derivative of g. So, that I will pass out, and then a is the initial guess, a is the initial guess, and then and from here I know that TOL tolerance is the tolerance. So, based on this one I can find the, now what I do is that I define maximum ITR. So, I just define maximum ITR, that I should not get my function to be iterated more than 100 times. Now, what I do is that now if my dg, whatever the function I am getting, the value of this function at a, because see from here I just want to clarify that in the earlier I can find evaluate f evaluate at a, the function dg at a. So, this can be written as you find dg, because dg is the function we are passing, and then I can write a only. So, that way also it will work. So, I will put if dg is greater than 1, suppose the value is coming 1, then I can write from here display. So, from here I can find the value of display, that for the given a, the modulus value g dash at a, the modulus value is greater than 1. So, d, it will treat this as a comma here. So, I will write instead of this, I will write dg at a is greater than 1. So, may not converge. That is it. So, this is the comment we are writing here, and then from here I will write return and then end. So, this will happen whatever the methods, the initial condition I am passing, I will check the value of this one. So, if this is not true, then I will put my ITR is equal to 0, I will put my x list. X list is the value of the roots at the each iteration. So, let us at first iteration its value is equal to a. So, whatever the initial guess I am giving, so that value will be saved in the x list at the first position. Now, from here I can write that f printf. So, that is the printf I can define, and then I can define the initial guess. So, start with the new line, initial guess. So, I can give the value of a, that is equal to, maybe I can write 7 ampersand this percentage sign, and then I can define 7.6 f. Then I can give my dg at the value of a. So, that is also same as equal to percent 7.6 f. Then after this the new line. So, I will write this, and then I will pass the value of a and dg at a. So, this value will be represented here. Now, what I do is that, so my let's because the, so this is my iterative method. Iterative method is x n plus 1 is equal to g of x n. So, I will give the value of x n, I will get the new value of x. So, in this case, so let us I get a new, that is equal to the g I pass, and this is equal to g a. So, this is I have found this value. Now, I will start my while loop. So, while a be absolute value of the value of f at a new. So, that is the value of f at a new is suppose greater than tolerance, because I know that if we are going close to the root, the value of f at the root will be 0. So, it close to 0. So, I am getting that its value is greater than, if it is greater than the given tolerance, you can. So, then I will should go inside the loop, and in this case I will type that if my ITR, the number of iteration, the max ITR, the maximum number of iteration is less than equal to ITR. So, in this it may happen that my iteration is keep going. So, if I say that my iteration is greater than equal to max ITR, then I should say that okay, stop here. So, I can write f print f, and then from here I can say that, or I can display maximum number of iterations reached. So, it will show that maximum number of iteration reached, and then it will break the program and then end. So, it will come out of the program. Otherwise, what should be done? It should find my A old is equal to A new. So, my A new should now go to the A old, then my A new should be G of A old. Now, it should get the value of. So, I am putting my method value A old at the G, and I am getting the new value. Now, I will write my ITR is equal to ITR plus 1, because it is incremented by 1, and then from here I can maybe show what is my error. So, I can write my error, absolute error, if it is needed, then A new minus A old, and then from here I can write my f print f. So, from here I can write that at iteration ITR is equal to percent D my A is this one. So, I can write my A 6.6F or maybe 7, I should write here 7 also, the same uniformity we should keep here, and then DG, the value of here I want my F at A. So, value of the error at A. So, from here I can write my F at A new. So, this is the value I am getting at my A. So, what is the value of that? And then I will put the AND to this while loop, and based on this one my F A new, that becomes value of the F at A new. So, that is the way we can find from here. So, now I can write here root. So, root will be my A new. So, that will be the root, because A new becomes A old, and after that I will put my iterative method, and from this method I will get the value of the A new. So, my A new will be there. So, if it come out from this loop, I will put this A new as a root of the equation, and this is my, I can write as F root. So, value of the function at the root. So, that is the way we can define, and from here I can also one thing I also want to put here X list. at ITR plus 1. So, that is I want to point A new, because I am also starting with 1 from here. So, that is why I am putting 1, because here it is starting from 0, it is 1. So, when it will be 1, it should be 2. So, that I am saving here. Now, I can save this code here, fix point, and then this is saved. Now, this is saved. So, now I want to do the calculation, open the main program. So, let us the open main program, and in the main program also we have to do some calculations, so that we should get the. So, this is I am writing the same main program. So, clear all CLC, and this is the function last time we have taken. Maybe I can comment this, and I will start with the new value or the new equation. So, in this case for the fixed point, so let us define f. So, f I am taking x raised to power cube minus 2 star x minus 8. So, that is I am defining the function here, and I am defining x exact. So, this is the value of the exact root for this equation. So, that is suppose I am taking 2.331. This is also approximate value of this root I am defining here. Now, I have to find out what is the g, because in the fixed point I need to find the value of g. So, g, if you see, we have done the same type of things in the lecture. So, and we found that if I take the g is equal to 2 star x plus 8. So, that is this value raised to power 1 by 3. Then in that case my value of the g will be less than 1. So, my dg will be, so from here I will get the value of dg. So, this will be 1 by 3 star 2 star x plus 8. So, that is the value we are getting raised to power 2 by 3. So, this is the derivative of the g I am getting. Okay. Now, in this case if I start with a is equal to suppose 1, and the tolerance I am giving you, that is 0.5 into e minus 5. So, let us take this one. So, that is the tolerance I am giving. Now, let us start finding the calling the function. So, I will find my root here, f root, then ITR iterations and x list. So, this is the argument I want from the function, and I am writing fixed point pt. So, that was the function I was calling. So, now my f is this, g is this. So, f, g and dg, f, g, dg, a and tolerance. So, this is the function I am calling from here. I will just save this one. Now, what I want to find the error. So, error will be E is equal to absolute value I am taking x list. So, this is the x list minus x exact. So, it will give you the value of E, the error at each iteration. Now, I will get my Q, that is the factor I am finding. So, my q is equal to I am defining as zeros the length, because I need 3 points always to find out the order of the convergence or the rate of the convergence. So, I will define my length of E. So, whatever the length is there minus 2, okay, and this one. So, that is the rows and the column. So, one column and the row, it means I am defining a column vector with all value 0 whose dimension is length of E, whatever the length of E is here, minus 2. Now, I am finding my q n minus 1. So, that is the value I am getting, and from here if you see from the previous lectures that I need to find this log. So, log means natural log I am taking E n plus 1. So, that is the E n plus 1 divided by E n. So, this is the value we are getting, this one. So, log E n plus 1 by E n and then divided by log E n divided by E n minus 1, this one. And here I have to put one more bracket, that is the bracket we are getting. Now, I want to plot these functions in the given program. So, I will write now from here I will define for I is equal to 1 to length of q. So, this is the length of q because I have gotten this value of the q here. So, this value I am getting, then I will write f print f the rate of convergence is, so that is equal to, I can write 4.2 maybe f, then I can write my new line and then I can define q I, this one, and then I can define the end. So, by this way we can define this function and that is my exact root. So, let us run this code and let us see that what is the error here. So, it is showing that the undefined function or variable x8 in the main program, this one. Okay. So, we should, this is a bisection program. So, I do not want to keep this program. Maybe I will, this is my main program. So, that is the function and this is 2x minus 8. So, that is the function we have defined, 2x plus 8, not minus, plus 8. So, 2x plus 8, that is the function we have defined. So, let us see now, again there is some error. Now, it is showing undivided function or variable n. Okay. So, here see from here initial guess is a is equal to 1 and the value of d at dg, the derivative g at 1 is 0.01. So, in that case, okay, we are going to get the root of the equation. Okay. So, that is the value of a, the root we are heading toward. So, this is my fixed point method we have defined. So, let us see that why it is not giving the value of dg. Okay, at iteration. So, I have to put ITR here, then the value of a and then the value of f nu and this one. So, that is the error here. So, I have saved this one. Now, we will write from here for two. So, this is length of E minus 1. So, this is the value we have taken, because this is the value with length. So, I will write my for loop, and is starting from 2 to length of E minus 1, and that is and. So, now let us see. So, that is my so now it is running, and that is the final solution. So, from here you can see that I will start it with my initial guess, that is 1, and at that place that value the dg was less than 1. So, it is going to converge. So, then I will get my value of a is this, value of the fa is this. So, with the iteration, after the 7 iteration, I will get the value of a, that is 2.3307, and the value of the function. So, this is the value of the function, I am not putting the absolute value. So, it is 0.00001. So, it is up to the tolerance. So, it is becoming less than the tolerance, and the rate of convergence is, I started with the initial guess. So, it is showing 0.49, then it is 0.48, 0.42, 0.19, then 0.13, then 0.12. So, in this case my rate of convergence is always coming less than 1, because it cannot be greater than 1. So, this is the way we found the rate of convergence. Because we know that in the fixed point methods, our rate of convergence is always unique, means either linear, the one. So, it may happen that sometime we will get the rate of convergence depending upon the value of that, what is the value of GA. So, based on the value of this GA, we can find the rate of convergence. So, in this case my rate of convergence is coming 0.12. So, maybe in the next class we will go for the other methods. So, this is the fixed point method. In the next class we will go for the Regula-Falsi and the Newton-Raphson method. So, thanks for viewing. Thanks very much.